let's talk about the Pieri rules. Now, this is going to use the labeled abacus point of view that we described earlier to talk about alternants. But first, let me define some notation. So, given a partition, so suppose I have, for example, 4, 3, 1. Recall we said a partition we often think of as being parts which add up together to give the answer. So now I'm going to represent this pictorially as follows. So 4 boxes in the first row, 3 boxes in the second row, and then I'm going to draw one more box. Okay. So this diagram here with in general lambda 1 boxes in the first row, lambda 2 boxes in the second row, and so on. So the general picture will look like this. So I'll draw lambda 1 boxes, lambda 2 boxes, and so on. So lambda 3 could equal lambda 2, and so etc. Okay, so this sort of picture would be what you would draw for lambda being a partition like this. Lambda L. Okay, so at least one. So this sort of diagram of lambda is sometimes called the Young diagram of lambda. Okay, now having drawn this picture, the next definition is rather intuitive. So we say that a partition lambda, so this is the notion of containment. When does one partition contain another? So given partitions lambda mu, we say mu contains lambda if the Young diagram of mu of the diagram of boxes contains the Young diagram of lambda. Okay, in other words, what does it mean? It says that, okay, let's give an example. So suppose I take the following partition. Then this partition contains, so this is the partition 3, 2, 1. This contains the partition whose Young diagram is 2, 2, for example. Okay, so in this example, we're going to say mu is the outer partition in pink, that's 4, 2, 1. Lambda, the inner partition, which is 2, 2. Okay, so observe the Young diagram. This has more boxes than the, not just more boxes, the boxes of lambda are contained inside the collection of boxes of mu. Now, what does this really mean? In general, if you write out mu1, mu2, mu n and so on, this just says that mu1 should be at least lambda 1. The second part, mu2 should be at least lambda 2 and so on. And finally, it also says that the number of parts of mu should be more than the number of parts of lambda. Okay, so when you keep going like this, at some point, you will run out of lambdas before you run out of mu's. So this is the condition, and length of mu is at least the length of lambda. Okay, so it's sort of intuitive what is meant by the containment relation. Now when we talk about containment, there is also a natural notion of difference. Okay, so now if mu contains lambda, then let mu contain lambda, we look at the difference, meaning the set of boxes that belong to mu but don't belong to lambda. So then mu mod lambda or mu by lambda is just the set of boxes in mu but not in lambda. Okay, the natural notion of a difference. Okay, now let's talk about some more interesting notions. So suppose I take a partition. So again, let's draw a picture here. So I have a 2, 3, 4, 5, 5, 3, 2. Okay, so here's my partition 5, 3, 2. Now, given this partition, let me do the following. I will sort of extend this top line and this vertical line here, and let me look at sort of the boundary of the partition, okay, by which I mean the path with vertical and horizontal segments which connects these two bits. Okay, so there's this sort of semi-infinite vertical line, then there are these horizontal segments, vertical, horizontal, vertical, 2 horizontals, 1 vertical, and semi-infinite horizontal segment. Okay, so this you think of as sometimes the boundary of lambda. Okay, and let me, having defined the boundary, let me talk about two sets of cells. So the first one, what should we call it? So let's look at the horizontal strip or the horizontal shadow. So what is the horizontal shadow of lambda? That is the collection of cells which have at least one one side in common with one of the horizontal segments of this boundary. So I mean, look at this boundary, it's got these horizontal segments, right? So there's this one is horizontal, here is a horizontal segment, horizontal. Now look at the cells which are not in lambda, which have at least one side on this horizontal segment, common with this horizontal segment. So what are the cells I'm talking about? So this bit is horizontal, so I'm talking about all these infinitely many cells here. Now look at this is the next horizontal part. Now there are two cells which are outside lambda which share that horizontal segment common. Now this guy has this horizontal segment, then there are two cells here. Okay, so this entire collection, and that's it. So this thing shaded in blue is what I will call the horizontal shadow. So okay, so this blue cells, they form what's called the horizontal shadow of lambda. Okay, so at least one side in common with one of the horizontal segments. Okay, another way of saying it is you just take the shape of lambda, and in each row you take the cells which are to the right, now just beyond the boundary, but you only go until as long as you have something on top of you. Okay, so in this case, for example, the second row, I start to the right of the shape of lambda. So I look at this cell first, and then I look at the next guy, but I don't take the next one. Okay, because that cell doesn't have a roof. There is nothing on top of it. The shape lambda is not on top of it. Okay, so that's the horizontal shadow. Now similarly, one can talk about the vertical shadow, which is the set of cells which have at least one side common with one of these vertical segments of the boundary. Okay, so let's see if we can draw it on maybe a different. Okay, maybe on the same one. So what's the vertical shadow? So here's one vertical segment. So this particular cell is also in the vertical shadow. Okay, so this cell is in the vertical shadow. Then let's see, here is another vertical. Okay, so this cell is in the vertical. Let's see, here's another one. Okay, and all of these guys. Now this is a semi-infinite just like that earlier one was semi-infinite on the first row, this is semi-infinite on the first column. Okay, so that's the vertical shadow of this original shape lambda. Okay, and some cells of course belong to both. Okay, now again as before, what does this really say? It just says you add, in each column, you look at it column by column. In each column, you add cells which are, below the the very last cell in that column, but only provided there is something on its left to support it. Okay. Now, okay, good. So why are we doing all this? So let's come back to what this is good for. So this is the first Pieri rule. So let's write that out. Pieri rules, there are two of them. So let me say Pieri rule number 1. Okay, so what does this say? It says fix n at least 1 and lambda some partition. So let me say lambda partition of D for some D. Actually, D can also be 0. Okay, in other words, lambda is the empty partition, if you wish. So lambda is a partition of D to some D. Then it says if you take the sure function S lambda in n variables x1, x2, xn and multiply it by the complete symmetric function h sub k. Okay, and now this is for all k at least 1. S lambda times hk, this product, is going to be the following. It's going to be expressible as a sum again of sure functions S mu, x1, x2, xn, and which are the mu's which appear in this on the right hand side. It's a sum over mu, where mu runs over elements of, so this is partitions of D plus k. Okay, so the original lambda was a partition of D. The mu's that you will get on the right hand side will be partitions of D plus k, such that the following happens. Mu contains lambda. Okay, the shape of mu contains lambda, and further the difference mu minus lambda is contained in the horizontal shadow. Shadow of lambda. Okay, so what this means is that so in that earlier diagram that we drew, so let's go back up there. So this was the original shape. So it says if you multiply the sure function, so the original shape in yellow is the shape lambda, and it says if you multiply that that sure function S lambda by the complete symmetric function h10, for example, then it says you can write it as a linear combination of sure functions, where the sure functions S mu which appear are the ones which are obtained by, you take lambda and then you make it bigger, right? Mu contains lambda, but you make it bigger in a very special fashion. You are allowed to add some additional boxes to the boxes of lambda, but you're only allowed to add boxes which lie in the horizontal shadow of lambda. Okay, So you look at all mu's which are obtained from lambda if you wish, right? Mu contains lambda means you can think of mu as take lambda and attach some extra boxes, but the newly attached boxes must all come from the horizontal shadow. Okay, only those boxes are allowed. Okay, so this is the rule, and let's just mention. So this has a sort of specific terminology. We say when this happens, we say that mu minus lambda is a horizontal strip. This is just terminology for when this happens. Okay, when mu contains lambda and mu minus lambda belongs, subset of the horizontal shadow of lambda, then you say, oh, mu minus lambda is a horizontal strip. Okay, and observe also that the number of boxes in the partition lambda was D, because it's a lambda was a partition of D, whereas the number of boxes in the partition mu is D plus K. So you are essentially adding K more boxes, okay, and you are adding K more boxes from the horizontal shadow of lambda, such that the final answer is again a partition. Okay, so this is the statement of the Pieri rule. Now, before we actually prove it, let's look at an example just to fix ideas on what is going on here. So suppose we take okay, so we're going to multiply two things. So let me just pick some. So if lambda is the following shape, okay, which is 2, 1. So let's just take something simple here. And if K is 3, okay, and let me assume that some n is large enough. So I have some large number of variables, say 10 variables. So now here's the question: what happens when I multiply the Schur function S lambda by the complete symmetric function H3? Okay. Now the Pieri rule says, first look at the horizontal shadow. Okay, in this case, the horizontal shadow is all of these, and this. Okay, so that's the horizontal shadow. Now, what are you supposed to do? You are supposed to add. So this is now the sum of all Schur functions as mu, where mu contains lambda, mu minus lambda. Well, we know how many boxes it has. It's supposed to be a partition of D plus K, right? Lambda in this case is the partition to 1. Okay. Now, mu minus lambda is in is, as we said, we called it a horizontal strip. Right? So this is contained in the horizontal shadow of. Okay, and has 3 boxes. Let's write it like this: mod of mu minus lambda is 3. Okay, that's supposed to be K in this case. So let's see how many ways can we do this. So let's try and attach 3 boxes to the boxes which are already in lambda. So lambda has 1, 2, 3 boxes. Now let's attach 3 more boxes to it such that it's fully in the horizontal shadow. So most obvious way of doing it, I attach all 3 in the same row. So this is one possibility. Okay, let's see what other term will I get. So this summation will have many terms in general. So here's the second term. I attach 2 from here and 1 from here. Okay, so this is the second possibility. Third possibility, and I start with mu. I attach 2 in this, then 1 in the other guy. Okay, fourth possibility, let's see, what else can I do? I attach, okay, can I attach 2 in the same row? Beyond this, I don't suppose so, because the horizontal shadow doesn't have that much room, right? The second and third rows only contain sort of 1 box each. So I can't really attach 2 in a given row anymore. Okay, so I do the next best thing, which is I attach 1 in the first row. Then I'm forced to do this. I there's only that much room left. I can only attach one in the second and one in the third. Okay. So these are all the shapes that I can get by starting with the original shape lambda and trying to attach 3 more boxes to it, such that the boxes I attach are all from the horizontal shadow. Okay, good. Now, one can then read out what these mu's are. So let's see what the mu, just have to read out the partition. So this is 1, 2, 3, 4, 5, 1. So here the partition is 5, 1. This partition is 4, 2. This is 4, 1, 1. This partition here is 3, 2, 1. Okay, so if you multiply the sure function S lambda corresponding to lambda equals 2, 1. So observe here the lambda that I started with is the partition 2 plus 1 or 2, 1. Okay, so I take S21 of x times H3. The answer is S51 plus S42. These are my answers. S of the partition 5, 1 plus sure function 4, 2 plus sure function 4, 1, 1 plus sure function 3, 2, 1. Okay, this is the S21 multiplied by H3. Okay, so all this is, here n is large enough. I have 10 variables. If I had fewer variables, then it's possible that, for example, if I only had 2 variables, then this sure function is just 0. Right? Similarly, this sure function is 0 in that case. Okay, so such degeneracies can arise. Okay, good. So now let's see how one would prove this rule.